So as was promised, in the last module towards the end, we just introduced the notion of sampling from a homogeneous Poisson process or classifying arrivals of a Poisson process into a finite number of types. But of course, now what we're going to do is we're going to do it somewhat more generally, in the sense that unlike what was discussed in the previous module, this time an arrival of a Poisson process, homogeneous Poisson process, would be sampled with a probability that is now allowed to depend on the time of that arrival. Or when we classify an arrival into k different types, the probability of its being classified as type I may depend or may be allowed to depend on the time of the arrival. But of course, the assumption of its being independent of other arrivals would be retained. So what we will show is that if we do this, then we of course decompose the original homogeneous Poisson process into a number of counting processes which add up to the original process, whose sum is the original homogeneous Poisson process. But what is important is that we are going to show that this decomposition actually gives us a decomposition into a number of independent, possibly homogeneous or non-homogeneous Poisson process. Homogeneous or non-homogeneous would depend on whether the probabilities, whether it is sampling probability or classification probabilities are allowed to be constant or are allowed to depend on the time of the arrival. So depending on that, the individual component processes would be homogeneous or non-homogeneous, but they would always be Poisson processes, independent, and their sum would be the original homogeneous Poisson process. Module 20 and the 6th module on Poisson process. So we describe here what is called sampling from a homogeneous Poisson process. We will discuss a more general phenomenon than what was discussed before, where a homogeneous Poisson process would be broken up into independent but possibly non-homogeneous Poisson processes. And what we had talked about earlier would be just a special case of this. So go back to the situation where each arrival of a homogeneous Poisson process, NT, with intensity lambda is recorded, sampled with a certain probability, or goes unrecorded or unsampled. But unlike before, where we assumed that the probability of an arrival being recorded stroke sampled is P, irrespective of the time of that arrival, we now assume that the probability that an arrival is recorded depends on the time of the arrival, or is allowed to depend on the time of the arrival. More specifically, we assume that the probability that an arrival is recorded is P of S, where P is a function, not a constant, if S is the time of that arrival. And of course, Qs equal to 1 minus Ps is the probability of the arrival at time S being not recorded. For every S, the number Ps is between 0 and 1. Of course, we retain the other assumption that whether a particular arrival is recorded or not is independent of other arrivals. We are now going to show that the two processes N1T and N2T that count the recorded and the unrecorded arrivals respectively give a breakup of the homogeneous process NT into two independent non-homogeneous Poisson process, or I should say possibly non-homogeneous, in the special case when the Ps is actually a constant P, as we had discussed before, both processes become homogeneous. Let us first fix a T positive and show that N1T and N2T are independent Poisson random variables. So for this, we will compute the probabilities, probability N1T equal to J, N2T equal to K for integers J and K non-negative. We will first condition on NT and calculate conditional probability of this event given NT equal to N. So the conditional probability that N1T equal to J, N2T equal to K, conditioned on NT being equal to N. Firstly, for N equal to 0, we don't have to do anything, because given NT equal to 0, both N1T and N2T have to be 0 with probability 1. nothing to do much. So we consider now n greater than or equal to 1. Now notice that by our definition, the number of recorded arrivals plus the number of unrecorded arrivals together, they add up to the total number of arrivals. In other words, n1t plus n2t is always equal to nt. Therefore, this conditional probability that n1t equal to j, n2t equal to k, given nt equal to n would be 0 unless j is an integer between 0 and n k is just n minus j, because given nt equal to n, the value of n1, possible values of n1 can only be from 0 up to n, in which case the possible value of n2 would be simply n minus whatever the value of n1 is. Okay, so this conditional probability is 0 unless j lies between 0 and n and k equals n minus j. Further, for j between 0 and n, the conditional probability that n1t equal to j and n2t equal to n minus j given nt equal to n, of course, equals the conditional probability that n1t equals j given nt equal to n. Because given nt equal to n, if n1t is j, n2t has to be n minus j. So we would now go on to compute the conditional probabilities, probability n1t equal to j given nt equal to n for j between 0 and n. So to do this, it's a very interesting idea. So to compute these conditional probabilities, let's ask the following question. Given n2 equal to n, nt equal to n, how does the process, the ns for s between 0 and 2, how does it look? Given nt equal to n, if you look at the process ns for s between 0 and t, first of all, it's just a step function. I mean, the paths are just step functions. Starts from n0 equal to 0 and reaches nt equal to n. Remember, nt equal to n is given. So paths are just step functions that start from 0 and reaches n at time t, and the way it goes from 0 to n is through n many jumps, each of size 1. That's what the typical path of ns for s between 0 and t would look like given nt equal to n. The only randomness is in the times of these n jumps, namely s1 less than s2, etc. less than sn less than or equal to t. However, we do know already, we had learned this before, that given nt equal to n, the arrival times s1 etc. up to sn are conditionally distributed like the order statistic u bracket 1 etc. u bracket n based on NIID uniform 0t random variables u1, u2, un. Using these ideas, we construct a process n tilde s, which I will call it n tilde s, s between 0 and t, which would exactly resemble, at least in distribution, the conditioned process ns s between 0 and t conditioned on nt equal to n. Okay, so how do we do this? So this is how it goes. Take NIID uniform 0t random variables u1, u2, un. Form the corresponding order statistic 0 less than u bracket 1 less than etc. u bracket n. Now I am going to define what n tilde s process is. Let n tilde s be a process indexed by time s between 0 and t, be defined as a step function starting from n tilde 0 equal to 0 and reaching n tilde t equal to n through n jumps, each of size 1, and these jumps take place at times u bracket 1, u bracket 2, etc. u bracket n. Okay, so that's the only place where there is randomness. Then the conditional distribution of the process ns for s between 0 and t given nt equal to n is no different from, is exactly same as the distribution of the process n tilde s for s between 0 and t as constructed by us. Suppose now we say that a jump of the process n tilde s, so we remove our attention from the process, conditional process ns for s between 0 and t given nt equal to, say, we remove our focus from there, instead look at the process n tilde s for s between 0 and t, which resembles in distribution the conditioned process ns given nt equal to n. So we now say that a jump of the process n tilde s for s between 0 and t would be colored red with probability Ps if the jump takes place at time s, independently of all other jumps. From what we have just now said, that the conditional distribution of the ns process for s between 0 and t conditioned on nt equal to n is exactly same as the distribution of the process n tilde s for s between 0 and t that we have constructed. Therefore, the conditional probability that the number of arrivals up to time t of the original n process that are recorded, that those number of arrivals are j conditioned on nt equal to n, would be exactly same as the probability that exactly j many jumps of the process n tilde s are read, because there an arrival is recorded with probability ps if the arrival takes place at time s, and here we are saying that a jump is colored red if with probability ps if the jump takes place at time s. So therefore, that conditional probability would be exactly the probability that there are j jumps of the process n tilde constructed by us which have been colored red. Now let's forget about this conditional process, conditioned process ns, condition on nt equal to n, focus entirely on the n tilde process. We have n jumps in the n tilde process, index bit for times s between 0 and t, each with a certain probability of being read, and we are interested in the probability of having exactly j read jumps. Okay. Now recall that the unordered set of jump times are, first of all, IID, uniform 0 to t random variables. Unordered set of jump times of the n tilde process. And when we count the number of read jumps, it doesn't matter whether we consider ordered or unordered set of jump times. It follows, therefore, that for each jump, the probability of its being colored red can be obtained simply by conditioning on when the jump happens, and is therefore given by p sub t equal to 1 over t 0 to t ps ds. So a jump is colored red with probability ps if the arrival or the jump happens at time s. Unordered set of jumps have IID uniform distributions, so therefore the probability of a jump being colored red is given by the average of ps or the integral of ps from 0 to t with respect to the density of uniform distribution on 0 to t, and that's exactly what it is. Further, a jump is colored red with probability p sub t independently of the other jumps. So this leads to the binomial probability that exactly j jumps are read is n choose j times pt to the power j times 1 minus pt to the power n minus j, and therefore what we have proved is that for any n greater than or equal to 1 and any j between 0 and n, the conditional probability that n1t equal to j given nt equal to n turns out to be the same, namely n choose j p sub t to the power j times 1 minus p sub t to the n minus j. It follows, therefore, from what we had done in the beginning, that for any pair of integers j greater than or equal to 0, k greater than or equal to 0, the probability of the event, joint probability that n1t equal to j, n2 equal to k, equals probability that n1t equal to j and nt equal to j plus k, which is equal to the probability that n1t equal to j given nt equal to j plus k times probability nt equal to j plus k. The first conditional probability, the first factor, the conditional probability, is what we had just now calculated. It's given by j plus k choose j, pt to the power j, 1 minus pt to the power k. And the second factor, probability that nt equal to j plus k, because nt is given to be homogeneous Poisson process, it's e to the minus lambda t to the power j plus k over j plus k factorial. Now a little bit of algebra, and this is what you get, e to the this is equal to the product of these two quantities. So what therefore it means, so this is a joint probability of x1t being equal to j and x2t being equal to k, but this joint probability is written as a product of two factors, one involving j, the other involving k. The one involving j is the probability mass function at j of a Poisson distribution with parameter lambda t pt, And the second factor involving k is the Poisson probability mass function at k of a Poisson distribution with parameter lambda t into 1 minus pt. Now, observing that lambda t pt, remember the definition of pt was 1 over t, 0 to t, integral ps ds. So, t pt would be integral 0 to t ps ds. So, lambda t pt would be lambda into integral 0 to t ps ds. Similarly, lambda t into 1 minus pt would be lambda into 0 to t qs ds, where qs is 1 minus ps. We conclude that n1t and n2t are independent Poisson random variables with the parameters lambda into 0 to t ps ds and lambda into 0 to t qs ds respectively. Now, the argument given above does not change if instead of considering n1t and n2t, we had taken any t1, fix it, take a t1 greater than or equal to 0, fix it, take any t positive and consider n1 t1 plus t minus n1 t1 and n2 t1 plus t minus n2 t1 instead of n1t and n2t. We would only need to work with the homogeneous Poisson process n t1 plus t minus nt1 instead of the original nt process, and keep in mind that the p and the q functions to be used now should be not the original p and q functions, but the functions p of t1 plus dot and q of t1 plus dot. Do this and then you can conclude that for t greater than or equal to 0, t1 greater than or equal to 0, t positive, n1 t1 plus t minus n1 of t1 and n2 of t1 plus t minus n2 of t1 are independent Poisson random variables with parameters lambda into t1 to t1 plus t ps ds and lambda into t1 to t1 plus t qs ds respectively. Further, since the total number of arrivals during the disjoint time intervals are independent, it is clear that the number of recorded or sampled arrivals during disjoint time intervals would also be independent, essentially meaning that increments of the n1 process over disjoint time intervals and increment of the n2 process over disjoint time intervals would be independent, and therefore they would be independent among all of them, because n1 is independent of n2, and the same would also be true for the number of unrecorded arrivals over disjoint time intervals. All these finally lead to the following result, which is that the process n1t and the process n2t are independent non-homogeneous Poisson processes with intensity function lambda 1t equal to lambda into pt, and lambda 2t is lambda into qt respectively. Of course, n1t and n2t would be homogeneous process in the special case when pt is identically equal to p, a constant, and only in that case. Now, there is a natural generalization of the above. Suppose each event, rather than just being recorded or non-recorded, suppose each event of a pp lambda nt can be one of k different types. For 1 less than or equal to I less than or equal to k, suppose the probability that an event is of type I, given that the event occurs at time s, is pis, independently of all other events. Here, for every s, the number pis lies between 0 and 1, and for each I, and then the sum of p1s etc. up to pks is 1 for all s. We then have, denoting nit to be the number of events of type I up to time t, for I equal to 1 to k, the processes nit as I varies between 1 and k are independent, possibly non-homogeneous Poisson processes for whom the intensity functions are lambda it equal to lambda into pit for 1 less than I less than k. Earlier, we have seen how a non-homogeneous Poisson process under certain conditions on its intensity function can be obtained as a time change of a homogeneous Poisson process. This required some conditions on the intensity function, namely that the intensity function should be such that its integral 0 to t is positive, etc., etc. Now, that was how you could get a non-homogeneous Poisson process as a time change of homogeneous Poisson process. Now, the following gives a method by which any non-homogeneous Poisson process with a bounded intensity function. So, this is a slightly different kind of condition on the intensity. It's a bounded intensity function. It can be obtained by sampling from homogeneous Poisson process. The technique is very, very useful in applications and is known as the technique of uniformization. So, it's very easy. Every non-homogeneous Poisson process with bounded intensity function lambda can be thought of as a sample from a homogeneous one. How? Well, here's the construction. Find a positive lambda such that lambda is dominated by lambda, the function, the values of the function lambda is dominated by lambda, the constant lambda. There would be such a lambda positive because I am assuming that the intensity function lambda is bounded above. Now consider a homogeneous Poisson process with rate lambda and record occurrence at time s with probability Ps equal to lambda s by lambda. Now, because by choice of the constant lambda, lambda s is less than lambda for every s, therefore Ps is less than 1. So, it makes sense. So, every occurrence at time Ts is recorded with probability Ps, which is lambda s over its bound lambda, upper bound lambda. Process of recorded occurrences this way will be a non-homogeneous Poisson process with intensity function lambda. So, this is sort of a way of constructing or realizing a non-homogeneous Poisson process with a bounded intensity as a sampling of a homogeneous Poisson process. This works provided the intensity function lambda satisfies the condition, namely that it's bounded above. Okay? This may not work otherwise. Concluding this particular module, let me say that we had just shown what we was promised, but then an interesting technique was used when we showed that when you say, for example, decompose a homogeneous Poisson process via sampling, the sampling probability may be allowed to depend on the time of the arrival or may not, may be a constant, doesn't matter. But in either case, what we were able to show was using a nice technique which again used that very, very important fact that we saw quite some time back, namely the conditional distribution of the time of arrivals up to time t conditioned on the total number of arrivals up to time t. That order statistic out of uniform distribution, that fact was once again used in this also. Using this, we were able to show that these component processes themselves turn out to be independent of each other. They turn out to be Poisson processes, homogeneous or non-homogeneous depending on whether the probabilities are allowed to depend on the time of arrival or are constants, but nevertheless they would always be independent Poisson processes. And at the end, to cap it off, basically what we did was, earlier we had seen how to get hold of a non-homogeneous Poisson process from a homogeneous Poisson process by the method of time change. Now here what we, towards the end, I talked about another very, very useful and important technique which is often very used quite frequently in applications, known as the technique of uniformization, whereby we showed that any non-homogeneous Poisson process whose intensity function is a bounded function can always be realized as sampling from a homogeneous Poisson process. The exact method was illustrated in the last few slides.